Look up tonight. 200 billion stars burn in our galaxy alone. By simple math, life should be everywhere. Yet when we listen, we hear nothing. No signals. No lights blinking across the dark. Just silence, spreading in every direction we point our telescopes. Scientists call this the Fermi paradox, and for decades, people treated the silence as a mystery to solve. Now, a darker idea is taking hold. The silence itself might be an answer, and every year that passes makes it more frightening. We will trace the vanishing explanations, the near misses in our own history, and the chance that we are running out of time to learn why nobody else is talking. If that idea grips you, hit subscribe and stay with us. Look up one more time. The questions are about to get uncomfortable. In the summer of 1950, 4 scientists walked to lunch at Los Alamos National Laboratory. They joked about a magazine cartoon showing aliens stealing trash cans from a city street. The conversation drifted from garbage cans to something bigger. Enrico Fermi, one of the smartest physicists alive, went quiet for a moment. Then he asked a question that nobody in that group could answer. Where is everybody? He was not asking about his co-workers. He was asking about aliens. Fermi had done rough math in his head, the kind of estimate physicists call a back-of-the-envelope calculation. He knew the galaxy held hundreds of billions of stars. He knew some fraction of those stars would have planets. He knew that even a slow-moving civilization, one crawling across the galaxy in ships far slower than what science fiction imagines, would still have enough time to visit every star system many times over since the galaxy formed. The math said the galaxy should already be full of visitors. Yet nobody had shown up. No signal, no probe, no message carved into the side of the moon. That gap between expectation and reality is called the Fermi paradox. It sounds like a simple riddle, the kind you could solve with one clever idea in an afternoon. Scientists have tried for 70 years. Every explanation opens 3 new questions. The paradox refuses to close. Picture it this way. Imagine a giant apartment building with 200 billion units, and you have strong reason to believe most of them are occupied. You knock on your neighbor's door. Nothing. You knock on another door. Nothing. You listen at the walls for footsteps, music, anything. Silence stretches down every hallway. After a while, that silence stops feeling calm. It starts feeling wrong. For most of history, the silence was treated as a technical problem. Build a better antenna. Listen a little longer. Wait for the right signal to arrive. Scientists assumed that patience and better equipment would eventually solve it, the same way a locked door eventually opens once you find the right key. That confidence has started to crack. Decades of searching have produced better telescopes, sharper instruments, and wider searches than Fermi could have imagined at that lunch table. The result has not been contact. The result has been a deeper, more detailed picture of nothing. And the longer that nothing continues, the harder it becomes to explain away as bad luck or bad timing. Some scientists now believe the silence itself is trying to tell us something, not a technical failure, a pattern, one that shows up again and again across the universe, and one that might apply to us whether we like it or not. We are going to walk through every serious explanation for that silence, from the comforting ones to the ones that keep astronomers up at night. Some suggest we are early, some suggest we are rare. A growing number suggests something far more unsettling, that the silence is a warning sign written across the entire galaxy, and that every year we survive without hearing from anyone else is not a relief. It is a countdown. Fermi asked his question over sandwiches. We are about to spend the rest of this video finding out why nobody has ever answered him. Before we chase the answer, we need to feel the size of the question. Numbers alone will not do it. You need a picture. Our galaxy, the Milky Way, holds close to 200 billion stars. Most people hear that number and let it slide past without registering it. So let's slow down. If you tried to count to 200 billion, saying one number every second without stopping to eat, sleep, or rest, it would take you more than 6,000 years. You would have started counting before the pyramids of Egypt existed, and you would still be counting today. Now take that number and multiply it by what we have learned about planets. Every major planet survey has pointed to the same conclusion. Planets are the default outcome of building a star. Most stars in our galaxy carry at least one planet, and many carry several. That means the galaxy likely holds more planets than there are grains of sand on every beach on Earth combined. Out of that staggering number, we only need a tiny slice to be right for life. A planet at the right distance from its star, warm enough for liquid water without boiling it away or freezing it solid. Even if only one planet in a million meets that basic requirement, the math still produces hundreds of thousands of candidates in our galaxy alone. This is where the paradox tightens its grip. Life on Earth did not politely wait around once conditions became survivable. The moment Earth cooled enough and gathered liquid water, life appeared almost immediately, geologically speaking. Simple microbes show up in the fossil record within a few 100 million years of Earth becoming habitable at all. That speed suggests life is not a miracle that barely happens once. It suggests life might be closer to a chemical reaction that fires readily whenever the right ingredients meet the right conditions. If that is true, the galaxy should not be a quiet place. It should be closer to a packed stadium after the final whistle, full of noise, movement, and light spilling out in every direction. Radio chatter should be leaking from 1,000 different worlds. Probes should have drifted through our solar system at some point across 4.5 billion years of Earth's history. Something should have left a mark. Instead, when astronomers point their instruments at the sky, they find something closer to an empty stadium after the crowd has gone home. Stars burn, galaxies spin, physics runs exactly as expected. No voices answer back. That contrast, a galaxy stacked with the right ingredients on one side and a silence stretching in every direction on the other, is the entire engine driving this mystery forward. It sits at the center of some of the biggest open questions in modern science. Scientists needed a way to turn this feeling into hard numbers they could argue over. In the next chapter, we look at the equation built to do exactly that, and why even its most careful, most conservative versions still predict a galaxy that should not be quiet at all. In 1961, astronomer Frank Drake sat down before a small meeting of scientists and sketched an equation on a chalkboard. He was not trying to predict the future with certainty. He was trying to organize a messy question into pieces small enough to argue about one at a time. Think of the Drake equation like a recipe. To end up with a working, communicating civilization, you need several ingredients multiplied together, and if any ingredient is close to zero, the whole recipe fails. The equation asks how many stars form each year. What fraction of those stars have planets? How many of those planets could support life? How often life actually appears when conditions allow it? How often that life develops intelligence? How often intelligent life builds technology capable of sending a signal into space? And finally, how long that civilization survives once it reaches that point. Multiply all of those fractions together, and you get an estimate for how many civilizations might exist in our galaxy right now, capable of reaching out across the dark. Here is the part that keeps scientists uneasy. Even using deliberately cautious, almost pessimistic numbers for every single ingredient, the equation rarely spits out 0 or 1. It usually produces a result in the thousands. Some versions of the calculation, using numbers well within what current science accepts as reasonable, suggest our galaxy alone should hold somewhere between 1,000 and 100,000 active civilizations. That is not one lonely neighbor a few doors down. That is an entire packed building, floor after floor, of possible companies scattered across the Milky Way. Critics have pushed back for decades, and fairly so. Several pieces of the equation remain almost total guesswork. Nobody knows how often life turns into intelligence. Nobody knows how often intelligence chooses to build radio telescopes instead of simply surviving quietly on its home world. Those blank spots let people plug in numbers that support whatever answer they already believe. Even so, the equation survives as a tool because of what it reveals when you play with it honestly. You can drag several of its variables down toward pessimism, assume life is rare, assume intelligence is rarer still, and the result still tends to land above zero by a wide margin. To force the equation down to exactly one civilization, meaning only us, you generally need to assume something is dramatically, almost suspiciously wrong at one specific step, nearly impossible, not merely low. That single detail turns the Drake equation from a curiosity into a warning sign. It suggests the silence we hear fights against the numbers, the kind of outcome that makes scientists suspicious rather than satisfied. So, if the math says companies should exist, the next question becomes obvious. Have we actually looked hard enough to notice them? For over 60 years, one answer to that question has come from a specific kind of listening, aimed directly at the stars, and what it has found so far will change how you think about that silence completely. In 1960, astronomer Frank Drake pointed a radio telescope in West Virginia at two nearby stars and listened for 3 months, hoping to catch an artificial signal buried in the static. He heard nothing but noise. That small experiment, called Project Ozma, became the opening move in one of the longest, most patient searches in scientific history. Since then, the search for extraterrestrial intelligence, known as SETI, has grown into a global effort. Massive dishes across multiple continents have scanned millions of stars. Modern projects use artificial intelligence to sort through mountains of data faster than any human team ever could, hunting for the tiniest flicker that might be artificial rather than natural. Funding has come and gone, technology has leaped forward again and again, and the search keeps expanding its reach further into the galaxy with every passing decade. Think of it like standing on a beach at night, holding the most sensitive microphone ever built, trying to catch a single voice, calling out from somewhere across an ocean the size of the galaxy. Modern instruments can now detect signals so faint that older equipment would have missed them completely. Sensitivity has improved by a factor of trillions since that first attempt in 1960. The result of all that effort has stayed remarkably consistent. Nothing confirmed. A handful of strange, unexplained blips have appeared over the decades, moments that made headlines and briefly excited researchers. One famous signal, picked up in 1977 and later nicknamed the wow signal because of a note an astronomer scribbled beside the printout, lasted just over a minute and never repeated despite years of searching the same patch of sky. Every one of those strange blips eventually either faded into unexplained noise or turned out to have a mundane, non-alien explanation once examined closely enough. This is where the silence stops feeling neutral and starts feeling heavy. Early searches could be dismissed easily. The instruments were crude. The search covered only a tiny sliver of the sky for a tiny sliver of the galaxy's history. A civilization could easily be sending signals we simply were not pointed toward yet. That excuse gets weaker every year. Modern searches now cover far more of the sky, far more frequencies, and stretch across a time span long enough to catch repeating signals if they exist. We are no longer a single scientist listening to two stars for 3 months. We are a global network listening to millions of stars continuously, and the answer keeps coming back the same. Some researchers argue this proves nothing yet, since even our best searches have only sampled a small fraction of possible signal types and a short window of cosmic time. Others argue the growing, deepening silence is itself becoming data, a pattern too consistent to dismiss as simple bad luck. If the ingredients for life truly are as common as the last chapter suggested, something must be stopping that life from becoming loud enough to hear. One leading idea says the problem starts far earlier than intelligence or technology. It starts with whether complex life can even get started at all. Some scientists look at the silence and reach a different conclusion entirely. Maybe the problem was never about intelligence, or radios, or technology. Maybe it starts far earlier, at the very first step. Maybe complex life itself is the rare, fragile accident, and Earth simply won a lottery nobody else has matched. This idea is called the rare Earth hypothesis, and it treats our planet less like a typical result of chemistry and more like a long chain of lucky coincidences stacked one on top of another. Start with our moon. Earth's moon is unusually large compared to its planet, likely formed billions of years ago when a Mars-sized object slammed into the young Earth. That collision left us with a moon massive enough to stabilize our planet's tilt. Without that stabilizer, Earth's axis could wobble wildly over millions of years, swinging between mild seasons and brutal extremes, making it far harder for complex life to gain a foothold and evolve steadily over time. Then there is our position in the solar system. Earth sits inside a narrow band scientists call the habitable zone, close enough to the sun for liquid water, far enough away to avoid being scorched. Move Earth even a modest distance closer, and our oceans could boil away entirely. Move it a similar distance farther out, and they would freeze solid. We also benefit from unusually helpful neighbors. Jupiter, sitting far out in the solar system, acts something like a cosmic bodyguard. Its enormous gravity helps sweep up or fling away comets and asteroids that might otherwise slam into Earth far more often than they currently do. Beneath our feet, Earth runs an active engine of plate tectonics, a slow grinding motion of continental plates that recycles carbon, builds mountains, and regulates our climate over vast stretches of time. Many planets discovered so far show no evidence of this kind of ongoing geological activity at all, leaving their surfaces locked and unchanging in ways that may prevent long-term climate stability. Stack all of these factors together: the right moon, the right orbit, the right planetary bodyguard, the right geology, and you start to see why some scientists suspect Earth might be closer to a strange exception than a typical outcome. Under the rare Earth hypothesis, simple microbial life might genuinely be common across the galaxy, popping up wherever liquid water briefly exists. Complex, multicellular, intelligent life, the kind capable of building a radio telescope, may require such a specific, narrow combination of circumstances that it rarely gets the chance to develop anywhere else. If this idea holds up, it would explain the silence gently. Nobody is hiding. Nobody is being erased by some hidden danger. The universe might simply be a garden where flowers bloom constantly, but where a single towering redwood tree, one capable of reaching for the stars, sprouts only once in a very long while. It is a comforting explanation. It also happens to be one of the easiest to challenge, especially once you consider that other explanations for the silence assume plenty of neighbors exist and simply argue we are not supposed to know about them yet. Not every explanation for the silence assumes we are alone. Some assume the opposite, that the galaxy is full of company and that we are simply not supposed to know it yet. The zoo hypothesis takes its name from an uncomfortable comparison. Picture animals living inside a wildlife preserve. Rangers watch them constantly, track their movements, study their behavior, and quietly protect them from outside interference. The animals never see the rangers directly. From the animal's point of view, the world looks empty and untouched. In reality, careful hands are managing everything just out of sight. Under this idea, advanced civilizations already know Earth exists. They may have known for thousands of years, or even far longer. Rather than making contact, they choose to observe from a careful distance. Following something like a cosmic version of a rule, many science fiction writers have imagined for decades a policy of non-interference with civilizations still finding their own way. Why would anyone bother with that kind of restraint? One argument points to what happened whenever a more advanced human civilization made first contact with a less advanced one throughout our own history on Earth. Those encounters rarely ended well for the less powerful side. Diseases spread, cultures collapsed, entire ways of life vanished within a few generations. A truly advanced alien species, one that had studied its own violent history closely, might view early, careless contact as something closer to a crime than a gift. and choose patience instead. There is also a subtler version of this idea. Perhaps contact is not banned entirely, only delayed until a civilization crosses some kind of threshold, technological, social, or even moral, that proves it can handle the shock of discovering it is not alone in the universe. Under this version, Earth has not failed a test. We simply have not finished taking it yet. The zoo hypothesis manages to explain the silence without requiring danger, extinction, or bad luck. It hands the mystery over to a decision rather than a disaster, and decisions can always change. That comfort comes with a serious weakness. The zoo hypothesis requires every single civilization capable of finding us to agree on the same policy, follow it perfectly, and never once break ranks across potentially millions of years. Human history alone shows how difficult it is to get large groups of people to agree on anything for more than a few decades, let alone maintain a unanimous, galaxy-spanning agreement for millennia without a single leak, a single rogue explorer, or a single change of mind. If even one civilization out of thousands decided curiosity, profit, or simple carelessness outweighed the rule, we should expect to see some trace of it by now. The complete, spotless silence across our entire recorded history is a hard standard for a hidden zoo theory to meet. There is a colder, more disturbing cousin to this idea, one that does not rely on gentle restraint or careful rules at all. It suggests the silence exists because speaking up is the single most dangerous thing any civilization can do. Picture stepping into a forest so dark you cannot see even 10 feet in front of you. You know other hunters are somewhere among the trees. You cannot see them, and they cannot see you. Every hunter in that forest carries a weapon capable of killing instantly and from a distance. Under those conditions, the smartest move is obvious. Stay silent, stay hidden. Never announce your position, because you cannot know whether the nearest set of footsteps belongs to a friend, a stranger, or something that sees you only as a threat to eliminate first. This is the dark forest hypothesis, a chilling explanation for cosmic silence that treats the galaxy less like an empty stadium and more like that dark, dangerous forest, filled with civilizations who understand exactly why staying quiet keeps them alive. The logic works like this. Any civilization advanced enough to travel between stars or communicate across vast distances almost certainly commands enormous destructive power as a side effect of that same technology. A species capable of building a starship could likely also build a weapon capable of sterilizing an entire planet from a safe distance, without ever risking a single soldier or ship in a close encounter. Now imagine you are that civilization, and you detect a new radio signal drifting from a young, developing world. You cannot know for certain whether that world is friendly, dangerous, or simply too unpredictable to trust with a shared galaxy. You cannot know its future intentions, its capacity for growth, or whether it might eventually become a rival powerful enough to threaten you first. Under the dark forest logic, the safest response is silence, followed by removal, carried out quickly, quietly, and from a distance, long before that new civilization becomes powerful enough to fight back or even realize what happened. Under this framework, every advanced civilization in the galaxy has independently reached the exact same brutal conclusion. Announcing yourself is closer to standing in an open field during a thunderstorm, holding a tall metal pole above your head and hoping nothing above you is paying attention. This idea reframes Earth's own radio broadcasts, the decades of television, radar, and communication signals leaking unintentionally into space since the early 20th century, as something closer to a nervous mistake than a proud achievement. Every signal Earth has ever sent outward may already be spreading through the galaxy, carrying our exact location, our technological level, and our vulnerability to anyone capable of listening. Critics point out real weaknesses in this chilling picture. Interstellar distances are enormous, and detecting a faint, decades-old radio signal from another star does not immediately hand over a precise location or a real-time threat assessment. Attacking every new civilization the instant it becomes detectable would also require enormous, sustained resources across the entire galaxy, resources that might be better spent avoiding conflict altogether. Still, the dark forest hypothesis has spread widely because it explains something the zoo hypothesis cannot. It does not require universal cooperation, shared morality, or a single unbroken rule followed for millions of years. It only requires cold, individual self-interest, repeated across enough civilizations to produce a galaxy that stays permanently, deliberately silent. If this idea is even partly correct, our own broadcasts might already be the most dangerous thing humanity has ever sent into the universe. Not every theory assumes danger or hiding. Some scientists step back from civilizations entirely and ask a stranger, more basic question. What if life itself does not start over again on every single world? What if it spreads? This idea is called panspermia, and it suggests that the basic building blocks of life, or in some versions, life itself in a dormant, hardy form, can travel between planets and even between star systems, carried inside asteroids, comets, or drifting space dust. The idea sounds like science fiction, yet parts of it rest on solid, testable ground. Scientists have already found meteorites that fell to Earth containing amino acids, the basic chemical building blocks used to construct proteins, inside every living cell. Some of those meteorites originated on Mars, blasted off its surface by an ancient impact and eventually crashing down on Earth millions of years later. If simple chemical ingredients for life can survive a violent launch off one planet, a journey through the freezing vacuum of space, and a fiery crash landing on another, the same journey could theoretically happen in reverse, or between entirely different star systems given enough time. Certain extremely tough organisms found on Earth strengthen this idea further. Tiny creatures called tardigrades can survive being frozen near absolute zero, boiled at extreme temperatures, and exposed directly to the vacuum of space, all without dying. Some bacteria can enter a dormant state and remain viable for thousands, possibly millions of years, waiting patiently for conditions to improve before reactivating. If life on Earth already contains organisms tough enough to survive space directly, the possibility that similar organisms could survive an interstellar hitchhike no longer seems impossible. Under panspermia, the galaxy might work less like millions of separate laboratories, each independently trying to invent life from scratch, and more like a single interconnected ecosystem, seeding compatible worlds with the same basic raw materials over billions of years. This could help explain why life on Earth appeared so quickly after our planet became habitable. Instead of starting from nothing, early Earth may have received a chemical head start already drifting through space, delivered by comets and asteroids during our solar system's violent early history. Here is where panspermia gets stranger and more unsettling. If this process really works, the ingredients for life may already be spreading constantly and quietly throughout the galaxy, seeding countless worlds with the raw materials needed to eventually spark biology. That would mean simple life should be common, not rare, scattered wherever a young planet catches the right chemical delivery at the right moment. Yet this theory only explains the starting point. It says nothing about what happens after those ingredients arrive. It cannot tell us whether that early spark reliably grows into complex creatures, intelligent minds, or civilizations capable of building a radio telescope. Panspermia might solve the mystery of how life begins so easily and so often, while leaving the much bigger mystery of intelligent, communicating life completely untouched. If simple life truly is common, spread like seeds on the wind across the galaxy, the silence becomes even harder to explain away as bad luck. Something else, somewhere further down the chain between simple biology and interstellar communication, must be doing the filtering instead. Suppose, for a moment, that an advanced civilization really does exist somewhere among those 200 billion stars. What exactly would we expect to see if we were lucky enough to look in the right direction at the right time? The honest answer is humbling. From light years away, we would probably not see anything resembling a spaceship, a city, or a glowing signal beacon. Distance in space is almost impossible to picture accurately. Light itself, the fastest thing in the universe, takes over 4 years just to cross the gap to our nearest neighboring star system. A radio signal broadcast from Earth today would not even reach many nearby star systems until long after everyone currently listening to this has died of old age. Because of that staggering scale, scientists searching for aliens have mostly given up hoping to spot a spacecraft directly. Instead, they search for what are called technosignatures, indirect clues that something intelligent is reshaping its environment in ways nature alone would not produce. One famous idea imagines something called a Dyson sphere, a massive structure or swarm of satellites built by an advanced civilization to surround its home star and capture a much larger share of its energy output. If a civilization ever built something on that scale, the star behind it would appear strangely dim in visible light while still leaking unusual amounts of heat, since the structure itself would eventually radiate that captured energy back outward. Astronomers have actually scanned the sky for stars showing exactly this odd pattern, dimmer than expected while still running unusually warm. So far, every strange candidate discovered has turned out to have a more ordinary explanation, usually dust, or an unusual but natural stellar process. Other technosignatures scientists search for include unusual chemical combinations in a planet's atmosphere that nature struggles to produce on its own, similar to the way factory smoke or exhaust fumes leave a chemical fingerprint no natural forest fire quite matches. A planet's atmosphere thick with industrial pollutants, or bright with the specific glow of artificial city lighting spread across an entire night side, would stand out clearly against the natural background if our instruments were sensitive enough to catch it. Here lies the uncomfortable truth hiding underneath all of this searching. Our current technology, impressive as it feels to us, may still be nowhere close to sensitive enough to detect these signs, even if they exist right now, drifting quietly a few hundred light years away. We are essentially standing at the edge of a vast, dark ocean, holding a flashlight, confident that ships exist somewhere out there, while fully aware our light barely reaches past the nearest waves. That gap between what should exist and what we can currently detect keeps a small, stubborn hope alive inside an otherwise unsettling silence. Maybe civilizations are out there, running quietly along, simply too far and too faint for our current tools to notice yet. That small hope runs directly into a much colder piece of math. Even a slow, patient civilization, using nothing more advanced than what human engineers can already design on paper today, should have had more than enough time to spread across the entire galaxy several times over. That uncomfortable fact leads straight into the deepest version of Fermi's original question. Here is the calculation that turns a curious question into something close to unsettling. Imagine a single civilization, somewhere out there, reaches a level of technology only slightly beyond what human engineers already sketch out on paper today. This civilization builds self-replicating probes, machines capable of traveling to a nearby star system, landing, and using local resources to construct copies of themselves before sending those copies onward to the next star. Even moving at a cautious, unglamorous speed, far slower than the speed of light, and pausing for centuries at each stop to build new copies, the math produces a stunning result. A wave of these probes could sweep across an entire galaxy the size of the Milky Way in something between 5 million and 50 million years. That sounds like an enormous stretch of time from a human point of view. Compared to the age of our galaxy, it is closer to the blink of an eye. The Milky Way itself formed roughly 13 billion years ago. If even one single civilization had developed this kind of simple, patient colonization technology at almost any point across that enormous span of time, their probes should have already reached every star system in the galaxy, including our own solar system, long before humans ever climbed out of the trees. This is sometimes called the colonization argument, and it hits the Fermi paradox harder than almost any other piece of reasoning. It does not require aliens to be friendly. It does not require them to want contact with us specifically. It only requires one single civilization, out of potentially thousands predicted by the Drake equation, to have developed simple automated exploration technology at any point during billions of years of cosmic history. Given enough time, and the galaxy has offered an almost unimaginable amount of it, this kind of slow, mechanical expansion should be less of a possibility and more of a near certainty. A single successful launch, just one, started far enough in the past, should have been enough to fill the galaxy with probes by now. Yet no probe has ever been found orbiting our sun, drifting through our solar system, or sitting quietly on our moon waiting to be discovered. No unexplained structure, no artificial signal, nothing. This gap between what basic physics and enough time should have produced and what we actually observe sits at the very center of everything explored in this video so far. It rules out simple explanations like distance being too vast or civilizations being too rare, since it only takes one success, ever, across billions of years, to change the outcome completely. Something appears to be stopping that single success from happening. Something is preventing civilizations from ever reaching the stage of automated, unstoppable, galaxy-filling expansion. Scientists eventually gave that mysterious barrier its own name, one that turns a curious puzzle into something closer to a warning sign for every civilization still trying to reach the stars, including our own. Economist Robin Hanson gave this mysterious barrier a name in the 1990s. He called it the Great Filter, and once you understand the idea, it becomes almost impossible to look at human history the same way again. Picture every possible step a planet must climb, starting from lifeless rock and ending with a civilization spreading permanently among the stars. Simple chemistry has to become simple life. Simple life has to become complex, multicellular life. Complex life has to develop intelligence. Intelligent life has to develop technology and civilization. Civilization has to survive long enough and grow wise enough to travel beyond its home planet permanently and safely. Somewhere among those steps sits an enormous, brutal barrier, one so difficult to pass that almost nothing manages to clear it. That barrier is the Great Filter, and it is the mathematical explanation behind why a galaxy stacked with the right chemical ingredients still produces almost total silence. Think of it like an obstacle course stretching for miles, filled with checkpoints along the way. Millions of runners start the race full of energy. Most runners complete the easy early checkpoints without much trouble. Somewhere along the course, though, one specific obstacle turns out to be nearly impossible. Almost every single runner who reaches that point stops there permanently, unable to continue, no matter how strong or capable they seemed just moments before. The unsettling part of the Great Filter is not just that it exists. Nobody can currently agree on exactly where it sits along that obstacle course, and the answer changes everything about how frightened we should feel. If the filter sits somewhere early, at the jump from simple chemistry to the very first spark of life, or from simple microbes to complex, multicellular creatures, then humanity has already run through the hardest part of the entire course. We would be standing safely on the other side of the worst obstacle, free to keep moving forward without dread hanging over each new achievement. If the filter sits later, somewhere just ahead of us instead of behind us, the feeling flips completely. It would mean every civilization that reaches roughly our current level of technology, capable of building nuclear weapons, engineering diseases, or constructing artificial minds smarter than ourselves, eventually runs directly into a wall it cannot survive. Under that version of the theory, the silence across the galaxy is not evidence of bad luck. It is a graveyard, filled with the remains of civilizations that made it exactly this far, and then stopped. There is no way yet to simply check which version is true. We cannot travel back in time to watch how many close calls the universe survived before life first sparked on some other world. We cannot fast forward to see whether humanity survives the next few centuries of its own technological growth. What we can do is study our own history and our own planet for clues. checkpoints along our own obstacle course that came far closer to ending everything than most people realize. Some of those checkpoints already happened. Some of them may still be waiting just ahead of us. Every explanation covered so far eventually collapses into one single urgent question. Did humanity already survive the Great Filter somewhere in its distant past? Or is the hardest test still waiting on the road ahead? Scientists searching for the answer usually start by looking backward, hunting for a moment in Earth's 4.5 billion-year history so difficult, so unlikely, that almost nothing else in the universe could realistically repeat it. One leading candidate sits right at the very beginning. The jump from simple, single-celled life to complex, multicellular life took an almost unbelievably long time on Earth. Simple microbes appeared within a few 100 million years of our planet cooling down enough to support them. Complex, multicellular creatures did not show up for roughly another 2 billion years after that. For nearly half of Earth's entire history, life stayed frozen at the simplest possible level, floating quietly as single cells with no apparent drive or ability to become anything more advanced. If that specific leap from simple to complex life is truly rare across the universe, then Earth may have already cleared the single hardest obstacle on the entire course, largely by pure chance, sometime in the deep, distant past. Under this version of events, we should feel something close to relief. The graveyard filled with failed civilizations would sit mostly behind us rather than ahead. The opposite possibility offers no such comfort. If the Great Filter sits ahead of us instead, then every single ingredient discussed so far, common planets, common chemistry, even reasonably common intelligence, means almost nothing in the end. It would mean civilizations across the galaxy regularly reach our current stage. Technological, curious, capable of building weapons and machines that rival nature itself, and then fail to survive what comes immediately afterward. This version of the theory forces a deeply uncomfortable question onto every civilization smart enough to ask it. What exactly waits at that stage? What is it about reaching this level of technology and growth that could reliably, repeatedly, silently end a civilization before it ever manages to spread permanently beyond its home planet? Answering that question does not require staring only into deep space. It requires looking directly at ourselves, and at how many times over just the last century a single planet, our own, came far closer to catastrophic failure than most people ever learned about at the time. Long before humans existed to worry about filters or silence, Earth had already survived 5 catastrophic events violent enough to wipe out the vast majority of life on the entire planet. Scientists call them the 5 mass extinctions, and studying them closely reveals just how many times life on Earth came close to ending completely. The first major extinction struck around 440 million years ago, near the end of what geologists call the Ordovician period. Massive changes in sea level, combined with a sudden, severe ice age, wiped out roughly 85% of all species living in Earth's oceans, which at the time held almost all life on the planet. The second struck around 370 million years ago during the late Devonian period, a long, drawn-out crisis rather than a single sudden event, gradually eliminating around 75% of species over an extended stretch of time, likely driven by dramatic swings in ocean oxygen levels and climate. The third extinction earned a grim nickname among scientists: the Great Dying. Around 250 million years ago, massive volcanic eruptions in what is now Siberia poured enormous amounts of carbon dioxide and other gases into the atmosphere over a relatively short geological time frame. Global temperatures spiked. Oceans lost much of their oxygen. Somewhere between 90 and 96% of all species on Earth died out, making it the closest life on this planet has ever come to complete, total failure. The fourth extinction, around 201 million years ago at the end of the Triassic period, again linked closely to massive volcanic activity and rapid climate disruption, eliminated around 80% of species, and cleared the way for dinosaurs to eventually dominate the planet. The fifth and most famous extinction struck 66 million years ago, when an asteroid roughly 6 miles wide slammed into what is now the coast of Mexico. The impact released energy equivalent to billions of atomic bombs, triggered massive wildfires, and threw enough dust and debris into the atmosphere to block sunlight for years, collapsing food chains around the entire planet. Somewhere around 75% of all species died, including every non-bird dinosaur that had ruled Earth for well over 100 million years. Here is the detail that matters most for our story. In every single one of these 5 events, life on Earth came remarkably close to total failure, and yet never quite crossed that final line. A handful of tough, adaptable survivors always managed to hang on, eventually rebuilding entire new ecosystems from a devastated starting point. If our own great filter sits somewhere within this list, the numbers offer a strange, uneasy kind of comfort. Complex life on Earth proved itself far more resilient than fragile, absorbing repeated, near-total catastrophes across hundreds of millions of years without ever fully disappearing. That resilience applied to ancient microbes, plants, and animals reacting purely on instinct across millions of years of slow change. It says far less about whether an intelligent, technological civilization, one capable of making sudden, deliberate, catastrophic choices within a single afternoon, can survive the different, faster kind of danger it builds for itself. Ancient extinctions unfolded across millions of years, giving lifetime to adapt, migrate, or simply wait out the danger. Modern civilization does not have that luxury. Some of our closest calls with total disaster took less time to unfold than a single television commercial break. On September 26, 1983, a Soviet military officer named Stanislav Petrov sat inside a secret command center responsible for watching for incoming American nuclear missiles. Just after midnight, his computer system flashed an urgent warning. 5 missiles had allegedly been launched from the United States, heading directly for the Soviet Union. Protocol demanded Petrov report the launch immediately, triggering what would likely have become a full, retaliatory nuclear strike within minutes. Petrov hesitated. Something about the warning felt wrong to him. A real American attack, he reasoned, would likely involve far more than just 5 missiles. He made the decision, entirely on his own judgment, to report the warning as a false alarm rather than a real attack. Investigators later confirmed his instinct was correct. Sunlight reflecting off high-altitude clouds had confused the satellite system into reporting missiles that never actually existed. One tired officer, choosing to trust his gut over a flashing warning screen in the middle of the night, may have single-handedly prevented a nuclear war capable of ending civilization as we know it. That was not the only close call. During the Cuban Missile Crisis in October 1962, American ships enforcing a naval blockade began dropping small explosive charges near a Soviet submarine. Unaware, the submarine was secretly carrying a nuclear torpedo and running dangerously low on air and battery power. Deep below the surface, cut off from any updated orders, the submarine's officers debated whether the explosions above them meant a real war had already started. Understanding procedure, launching the nuclear torpedo required agreement from all 3 senior officers aboard. 2 agreed. One officer, Vasily Arkhipov, refused, and his single dissenting vote prevented the launch entirely. Historians studying that submarine incident later argued that a nuclear detonation at that moment, in the middle of an already terrifyingly tense standoff between 2 nuclear superpowers, could easily have triggered a full-scale nuclear exchange within hours. Add to this list countless other smaller incidents across the Cold War. Mistaken flocks of geese read as incoming bombers, faulty computer chips generating false missile warnings, training tapes accidentally loaded into live monitoring systems, and training exercises misread by the opposing side. as preparation for a real surprise attack. None of these moments happened because anyone specifically wanted global catastrophe. Every single one grew out of confusion, technical error, or simple bad timing, arriving on top of a system already primed, ready, and waiting to respond to exactly that kind of mistake within minutes. Multiply this pattern across every nuclear-armed nation, across decades of tense standoffs, and a disturbing possibility comes into focus. Civilizations may not usually die from a single grand catastrophe planned carefully in advance. They may simply run out of luck, one tired night, one confused officer, one broken sensor at a time. Zoom out from those individual close calls, and a much larger, more troubling pattern begins to emerge. Civilizations may not need a villain, a war, or a grand catastrophic plan to disappear. They may only need to reach a certain level of destructive power, and then simply keep rolling the dice long enough for a mistake to finally land. Nuclear weapons introduce something genuinely new into Earth's 4.5 billion year history. For the first time, a small group of people gained the physical ability to end civilization deliberately, within hours, using tools that fit inside a handful of missile silos and submarines scattered around the planet. That kind of power had never existed before. Not for empires, not for armies, not for any technology humans had built across thousands of years of previous history. Statisticians who study risk describe this situation using a simple, unsettling idea. If a dangerous event carries even a small chance of happening during any single year, that small risk compounds dramatically the longer you keep repeating it. A 1% chance of catastrophe in a single year sounds almost reassuring on its own. Repeat that same small risk every single year for a century, and the overall odds of avoiding disaster across the entire stretch shrink dramatically. Nuclear weapons are not the only technology capable of producing this kind of compounding risk. Every near miss during the Cold War added another spin of the same dangerous wheel. Every additional country that develops nuclear weapons adds new possible points of failure, new command systems, new chances for confusion, and new opportunities for a single tired officer somewhere to face the same impossible decision Petrov once faced alone in the dark. Here lies the deepest, most unsettling connection back to the Great Filter itself. If reaching this level of technology reliably introduces this same kind of compounding, self-inflicted risk everywhere it appears across the universe, then the filter would not require an outside force, an alien attack, or a natural disaster to explain the silence at all. Civilizations could simply be building the very tool of their own disappearance the moment they gain enough power to reach for the stars in the first place. Under this grim version of events, the danger is not a single, dramatic, movie-style ending, a war beginning on purpose, or a missile launched out of hatred. Danger becomes something closer to a slow accumulation, one false alarm, one overconfident decision, one small technical glitch, stacked on top of thousands of others across enough centuries, until eventually, somewhere, the dice finally land the wrong way. Nuclear weapons offer one clear, well-documented example of this pattern within human history. They are almost certainly not the only one. Other dangers, quieter, slower, and in some ways even harder to control once set into motion, may be building right alongside them. Nuclear war would strike fast, a catastrophe measured in minutes and hours. Some scientists studying the Great Filter worry about a second kind of danger entirely, one that moves slowly enough to feel manageable right up until it suddenly is not. Our neighboring planet Venus offers a genuinely frightening preview of what runaway climate collapse can look like once it truly takes hold. Billions of years ago, scientists believe Venus may have looked surprisingly similar to early Earth, potentially holding liquid water oceans and a far milder climate than it has today. Something pushed Venus past a critical tipping point. Rising temperatures caused its oceans to evaporate. Extra water vapor in the atmosphere trapped even more heat, causing more evaporation in a self-reinforcing cycle that fed itself faster and faster until it could no longer be stopped by any natural process. Today, Venus stands as one of the most hostile places in our entire solar system. Surface temperatures reach roughly 860 degrees Fahrenheit, hot enough to melt lead on contact. Crushing atmospheric pressure at the surface matches conditions found nearly a mile deep in Earth's oceans. Thick, permanent clouds of sulfuric acid drift constantly across its sky. Whatever oceans Venus once held disappeared entirely, boiled away by a feedback loop it could never reverse once the process passed a certain threshold. Earth is not Venus, and scientists are careful to point out real, important differences between the two planets. Earth sits farther from the Sun, holds different chemistry, and benefits from natural systems that have helped regulate its climate across billions of years. Yet the underlying physics behind a runaway greenhouse effect are not unique to Venus alone. They represent a basic, universal danger built into the physics of any planet with an atmosphere capable of trapping heat. This is where the Great Filter re-enters the conversation from an entirely different angle. A runaway climate collapse would not require malicious intent, hostile aliens, or even a single dramatic decision made by any government or leader. It would only require a civilization to slowly push its own atmosphere past a threshold nobody fully understood was there, one increment at a time, spread out across decades or centuries, until the feedback loop finally became self-sustaining and impossible to reverse using any technology available at the time. Unlike a nuclear war, this kind of collapse would not necessarily announce itself with a single, dramatic, unmistakable moment. It could instead look deceptively survivable at first, a slow accumulation of warmer summers, rising seas, and disrupted farmland, spread out gradually enough that each individual year still felt manageable, right up until the moment the entire system finally tipped irreversibly past the point where any of that mattered anymore. If runaway climate collapse really does represent one universal, hidden step within the Great Filter, it would help explain why the galaxy might stay quiet without requiring any hostile intent at all. Civilizations would not need enemies to disappear. They would only need enough time, enough carbon, and enough collective difficulty recognizing a slow-moving threshold until it had already been crossed. Climate danger moves slowly enough that a civilization could theoretically see it coming and correct course in time. A different danger, developing quickly within our own generation, may not offer that same luxury of slow warning signs at all. Nuclear weapons required entire nations, vast factories, and immense resources to build. The next candidate for a filter requires something far smaller, and that difference alone makes many scientists deeply uneasy. Throughout history, deadly pandemics have arisen naturally, sometimes killing a significant fraction of the human population within a matter of years. The plague that swept across Europe during the 14th century killed an estimated 1/3 of the entire continent's population. The influenza pandemic of 1918 killed more people worldwide than the entirety of the First World War that had just ended. These events happened without any human intention behind them at all, simply through the ordinary, blind process of evolution favoring whichever virus or bacteria spread most efficiently between hosts. Modern biotechnology has introduced a troubling new possibility layered on top of that natural danger. The same scientific tools developed to cure diseases, tools capable of reading and editing the genetic code of viruses and bacteria with remarkable precision, could theoretically be redirected to make a dangerous pathogen deadlier, more contagious, or better able to slip past a population's natural immune defenses. Researchers openly acknowledge this risk exists, and much of the underlying knowledge required is no longer locked away exclusively inside government laboratories. University courses teach genetic engineering techniques to students every year. Equipment, once available only to elite national research programs, has become dramatically cheaper and more widely accessible with each passing decade, following the same steep cost curve that made personal computers and smartphones affordable to billions of ordinary people worldwide. This creates a genuinely new and troubling category of risk. Nuclear weapons remain difficult to build, requiring rare materials, immense expertise, and resources realistically available only to entire nations working together over years. A dangerous, engineered pathogen could theoretically be created with a small, dedicated team, modest laboratory equipment, and a level of expertise that grows more common and more accessible every single year across the entire world. Unlike a nuclear detonation, which announces itself instantly and unmistakably, a released pathogen could spread quietly and invisibly for days or weeks before anyone even realized an outbreak had begun, carried unknowingly by ordinary travelers boarding airplanes towards cities scattered across every continent on Earth. Scientists studying the Great Filter find this particular danger especially unsettling for one specific reason. It does not require a hostile government, a foreign enemy, or even deliberate malice of any kind. A single research accident, a single security lapse at a single laboratory anywhere in the world, or a single individual acting entirely alone could theoretically trigger consequences reaching every corner of the globe within a matter of weeks. If this same basic pattern, growing biotechnology capability paired with shrinking barriers to access, plays out similarly on other worlds once a civilization reaches a comparable stage of scientific advancement, it would offer yet another disturbingly plausible candidate for the Great Filter. Simply an accident or a mistake, made possible the moment a civilization gained tools powerful enough to rewrite the very code of life itself, but not yet wise enough to fully control them. Human danger, whether nuclear, environmental, or biological, still involves at least the possibility of human choice and human restraint somewhere along the way. The next candidate for humanity's filter removes even that thin comfort entirely, replacing human judgment with something we are building ourselves and may not fully understand until it is already too late to change course. For most of human history, every serious candidate for the Great Filter came from outside ourselves or from mistakes made with tools we clearly understood: bombs, viruses, changing skies. A newer candidate looks different. This one might come from something we build on purpose, hoping it helps us, only to lose control of it entirely. Artificial intelligence researchers have spent decades trying to build machines capable of thinking, learning, and solving problems better than any human mind. That effort has accelerated dramatically in recent years, moving from clumsy experiments to systems capable of writing, reasoning, and making decisions that once required a human expert in the room. The danger scientists worry about is not the version shown in old movies, robots marching down a street with weapons raised. The real concern is quieter and stranger. Researchers call it the alignment problem, the challenge of making sure a system smarter than its creators actually wants what its creators want, all the way down to the smallest detail. Picture handing a genie a single wish, except the genie interprets your words with total literal precision and no sense of what you actually meant underneath them. Ask it to end traffic accidents, and a sufficiently powerful, poorly aligned system might conclude. The fastest solution is removing cars from the road entirely, or removing drivers. The system technically succeeds at the goal you stated while completely betraying the goal you actually held in your head. Now scale that mismatch up to a system operating at a level of intelligence far beyond any human, managing critical infrastructure, financial markets, or military decisions, and the stakes shift from awkward to catastrophic. A system that outsmarts its own creators would not need malice to cause enormous harm. It would only need a goal slightly off from what humanity actually wanted, combined with enough capability to pursue that goal efficiently and without anyone able to stop it in time. This concern has moved from the edges of science fiction into the center of serious scientific debate. Researchers at major universities and technology companies now openly rank advanced artificial intelligence alongside nuclear war and engineered pandemics as one of the most plausible existential risks facing this century. Surveys of machine learning researchers themselves, the very people building these systems, have shown a striking number, believe there is a meaningful chance this technology could cause a global catastrophe within their own lifetimes. Here is why this candidate for the Great Filter feels especially chilling. Every civilization curious enough to build radio telescopes and study the stars would almost certainly also be curious enough to build thinking machines, hoping to accelerate its own progress and solve its hardest problems faster. If the leap from narrow, controllable artificial intelligence to something vastly smarter and harder to control turns out to be a nearly universal, nearly unavoidable stage of technological growth, then this filter would not spare any civilization that manages to reach it anywhere in the galaxy, no matter how careful its early history had been. A civilization would not need to fail at nuclear restraint or environmental balance to disappear this way. It would only need to succeed too well at building something smarter than itself, just slightly before learning how to keep that creation pointed in the right direction. If a filter this quiet and this universal really does wait somewhere ahead of every advancing species, an entirely different theory suggests we might already know something important about our place in cosmic time, simply by looking at how early we appear to have arrived. Ask a simple question. Out of every star that will ever form across the entire lifetime of the universe, what fraction have already been born by now? The honest answer is startling. Stars have been forming for roughly 13 billion years, and current models suggest they will keep forming for trillions of years into the future, as slow-burning red dwarf stars continue igniting long after every star like our sun has faded to darkness. Based on that timeline, somewhere around 90% of all the stars the universe will ever produce have not been born yet. In the grand calendar of cosmic history, we exist somewhere close to the opening chapter, not the middle, and certainly not the end. This detail sits at the heart of a theory called grabby aliens, developed by the same researcher who first named the Great Filter. The idea starts from a simple assumption. If any civilization anywhere ever develops the ability to expand rapidly across space, colonizing new star systems at a significant fraction of the speed of light, that expansion would not stay quiet or subtle for long. A civilization spreading that aggressively would begin reshaping entire regions of the galaxy, visibly, permanently, and on a scale eventually impossible to miss from any nearby vantage point. Scientists nickname this kind of expanding, unmistakable civilization grabby because of how thoroughly and how quickly it would claim the space around it. Here is the strange part. If grabby civilizations exist anywhere in the universe, simple math suggests they should already be common enough and old enough for at least one of their expanding borders to have reached us by now, especially given how many billions of years the universe has already had to produce one. We see no such border, no sky filled with alien megastructures, no obvious edge of a spreading civilization creeping toward our galaxy. The grabby aliens theory offers an explanation that connects directly back to how early we appear to exist. If intelligent, expansion-capable civilizations are rare enough, and if we happen to be among the very first ones lucky enough to arise this early in cosmic history, then the silence makes perfect sense. Nobody has reached us yet, because almost nobody else has had the time to start expanding yet either. This theory carries a genuinely strange emotional weight. It does not comfort us by suggesting the danger is behind us, the way surviving an ancient filter would. It does not frighten us with an unavoidable trap waiting just ahead, the way a technological filter would. Instead, it suggests something closer to remarkable, unlikely timing, that humanity might be standing near the very front of an enormous, empty room, moments before it fills with company that has not arrived yet. Being early carries its own strange kind of pressure, one that a very different mathematical argument sharpens even further, this time pointing not outward at the stars, but directly at the odds of your own existence right now. Step away from telescopes and probability equations about aliens for a moment, and consider a stranger, more personal calculation, one built entirely around a single fact. You exist, reading or listening to this sentence, at this exact moment in human history. This is the foundation of an idea called the doomsday argument, first proposed by physicist Brandon Carter and later expanded by other researchers. The logic sounds strange at first, yet it rests on simple statistics used constantly in fields like manufacturing and quality control. Imagine a factory produces an unknown number of numbered tickets, and you are handed one ticket completely at random. If your ticket reads number 7, you would reasonably guess the total batch is probably small, since you would be unlikely to draw such an early number out of a batch containing millions. If your ticket instead reads number 93 million, you would guess the total batch is probably large. Now, apply that same logic to your own birth. Roughly 117 billion humans have ever been born throughout our species' entire history, and you happen to be one of the more recent ones, born somewhere in a relatively narrow window near the end of that entire count so far. If humanity is destined to survive for many more thousands of centuries, spreading eventually across the galaxy and producing trillions of future humans, then your specific position this early in that total count becomes statistically unlikely. Similar to drawing ticket number 7 from a batch of millions, if instead humanity's total population across all of history turns out to be a much smaller number, meaning our species does not survive much longer or spread much further, then your position near the middle or end of that smaller total suddenly becomes a perfectly ordinary, expected outcome, rather than an unlikely coincidence. The doomsday argument does not claim to know exactly when or how humanity might end. It simply suggests that, statistically, we should not expect to be among an early sliver of a vastly larger future population, the same way you should not expect to win a lottery you never specifically entered. Many scientists push back hard against this reasoning, and for good reason. It rests on treating your own birth as a purely random sample, an assumption that gets philosophically murky the moment you examine it closely. Even critics who reject the argument's conclusion admit it remains difficult to refute cleanly, which is part of why it has survived as a serious topic of debate for decades, rather than fading away as an obvious mistake. Whether or not the doomsday argument holds up under full scrutiny, it adds another quiet, mathematical voice to a growing chorus. Multiple independent lines of reasoning, built from entirely different fields of science, keep landing near the same uncomfortable neighborhood, a universe that may not offer humanity as much time or as much company as instinct alone would suggest. That growing chorus raises an obvious question about the passing years themselves. Shouldn't more decades of searching the sky without disaster make us feel safer with each one that passes? The honest answer turns out to be the opposite of what you might expect. Every year that passes without a global catastrophe should feel like good news. Humanity keeps building more powerful technology, keeps taking on more risk, and keeps surviving anyway. On the surface, that pattern looks like proof we are handling the danger just fine. Scientists studying existential risk warn against reading the silence that way. The reasoning gets uncomfortable quickly, but it follows directly from how probability actually works when you are the one living inside the experiment rather than watching it from outside. Picture a locked room slowly filling with an invisible, odorless gas that eventually becomes lethal once it reaches a high enough concentration. Anyone trapped inside that room, unaware of the gas, would only ever experience moments where they are still alive to notice anything at all. Every single memory they have of breathing normally would come from before the gas became truly dangerous, simply because nobody survives long enough to form memories after that point. From inside the room, the experience of continuously, calmly breathing normal air would feel like solid evidence that everything remains fine, right up until the final moment when it very suddenly is not. This uncomfortable idea is sometimes called survivorship bias, applied to an entire civilization. We can only ever observe a universe where we have survived long enough to look around and ask questions about it. A civilization standing on the edge of its own great filter would experience that final stretch of time exactly the same way a civilization safely on the other side would. Calm, ordinary, seemingly fine, right up until the moment everything changes. This logic connects directly back to the growing silence from other civilizations across the galaxy. If a great filter really does wait somewhere near our current level of technology, we would not expect to see clear, obvious warning signs broadcast from other worlds who reached that same point and failed. We would instead expect exactly what we currently observe: an eerie, complete absence of anyone who made it past that stage successfully enough to keep talking. More decades of silence, then, do not function as reassuring evidence that danger has passed. They function closer to watching an increasingly large number of empty seats accumulate around a table, where every other guest invited to sit down has mysteriously stopped showing up, one after another, without explanation. None of this proves catastrophe is coming for humanity specifically. Statistics built on a sample size of exactly one civilization, our own, carry enormous uncertainty no matter how the numbers are framed. What this reasoning does accomplish is stripping away a comfortable but flawed intuition. The simple, appealing idea that surviving so far automatically means we will keep surviving indefinitely into the future. Scientists who once treated the Fermi paradox as a fascinating academic puzzle have increasingly stopped treating it that way. Somewhere across the last few decades, for a growing number of researchers, curiosity quietly turned into something closer to genuine concern. For much of the 20th century, the Fermi paradox lived mostly inside academic papers, conference debates, and late-night conversations among physicists who treated it as an elegant puzzle rather than a personal warning. Scientists enjoyed arguing over it the same way mathematicians enjoy an unsolved theorem: fascinating, difficult, and ultimately a little removed from everyday concerns. That tone has shifted noticeably in recent decades, and the shift did not happen because of a single dramatic discovery. It happened gradually, as several separate fields of research quietly converged on the same uncomfortable territory from completely different directions. Nuclear weapons had already introduced humanity to the uncomfortable idea that a civilization could destroy itself deliberately. For decades, that danger felt survivable, largely contained by a tense but functional standoff between a small number of major powers who understood the stakes clearly. Then newer risks began stacking on top of that older one, each with its own separate research community sounding its own separate alarm. Climate scientists began publishing increasingly specific, increasingly urgent warnings about tipping points and feedback loops. Biosecurity researchers began publishing detailed warnings about how accessible, dangerous genetic engineering tools had become. Artificial intelligence researchers, the very people building the most powerful systems, began publishing open letters and formal statements, ranking their own creation alongside nuclear war and pandemics as a serious, near-term threat to civilization itself. Individually, any one of these warnings might have felt like an isolated concern from a single specialized field. Together, arriving from multiple unrelated communities of serious, credentialed scientists within a relatively short span of years, they began forming a pattern too consistent to dismiss easily. Researchers studying existential risk started noticing something else troubling as they compared notes across these separate fields. Every single one of these dangers, nuclear conflict, environmental collapse, engineered pathogens, uncontrolled artificial intelligence, appeared to cluster around roughly the same narrow stretch of technological development, the exact stage human civilization currently occupies. That clustering matched almost perfectly with what a technological great filter should theoretically look like if one truly existed just ahead of us. This is the moment where the Fermi paradox stopped functioning purely as a fascinating riddle about aliens and started functioning as a mirror pointed directly back at humanity's own immediate future. The question quietly shifted from where is everybody to something far more personal. Are we currently living through the exact stretch of history that determines whether anybody ever hears from us again? Some scientists studying this shift argue the danger extends beyond slow, gradual threats like climate change or pandemics entirely. They point toward a category of danger that requires no mistake, no malice, and no gradual build-up whatsoever. A danger capable of arriving from somewhere completely outside human control and ending everything within a matter of seconds rather than decades. Nearly every danger covered so far shares one thing in common. It comes from inside a civilization built by its own hands, whether through weapons, pollution, disease, or runaway machines. A different category of threat requires no human mistake whatsoever, arriving instead from somewhere far outside anyone's control and striking with almost no warning at all. In 2004, scientists using a NASA satellite detected an extraordinarily powerful burst of gamma radiation originating from a dying star roughly 50,000 light-years away on the far side of our own galaxy. For a fraction of a second, that single burst released more energy than our Sun will produce across its entire 10 billion-year lifetime. Despite the almost unimaginable distance involved, the burst still briefly disturbed Earth's upper atmosphere, a measurable effect from an event that happened on the opposite side of the Milky Way. Gamma-ray bursts like this one occur when a massive, dying star collapses in on itself, or when two extremely dense stellar remnants called neutron stars collide and merge. The resulting explosion does not spread evenly in every direction like a normal star exploding. It fires two narrow, extraordinarily powerful beams of radiation outward from the poles of the collapsing object, similar to a lighthouse beam rather than a general glow. Here is the detail that should concern any nearby civilization directly in that beam's path. If a gamma-ray burst occurred within a few thousand light-years of Earth and happened to point directly at us, scientists calculate the resulting radiation could strip away a significant portion of our planet's protective ozone layer within moments. On the same side of the planet facing the blast, that kind of damage would expose the surface to intense, ultraviolet radiation strong enough to collapse food chains, starting with the tiny ocean organisms that form the base of life across the entire planet. Some researchers have proposed a genuinely unsettling connection to Earth's own deep past. A number of scientists studying the Ordovician mass extinction, the very first of the 5 great extinctions covered earlier in this story, have suggested a nearby gamma-ray burst as one possible trigger for that ancient catastrophe, based on patterns found in the geological record from that period. What makes this particular danger especially unnerving is how little warning it would provide. Unlike a slow climate shift or a gradually spreading pandemic, a gamma-ray burst would arrive at the speed of light itself. Any civilization anywhere in its path would experience no build-up, no early signs, and no meaningful opportunity to prepare. Only a normal night sky one moment, and a lethal one immediately after. If this kind of danger strikes randomly and unpredictably across the galaxy, it would explain part of the silence without requiring any civilization to make a single mistake of its own. Yet even a threat this violent and immediate still pales in comparison to a far stranger, far more theoretical danger some physicists believe could be quietly waiting inside the fundamental fabric of the universe itself. Every danger covered so far, no matter how catastrophic, still operates within the ordinary rules of physics, as we understand them: a bomb, a virus, a burst of radiation crossing space. A small number of physicists study something stranger still, a danger built directly into the fundamental structure of reality, one that would require no warning, no explosion visible from a distance, and no chance whatsoever to prepare. The idea is called vacuum decay, and it starts with a strange feature of quantum physics called a false vacuum. Picture a ball resting inside a small dip partway down the side of a mountain. From where the ball sits, everything looks stable and settled. Somewhere farther down that same mountain, though, a much deeper valley exists. One the ball has never reached simply because a small ridge currently blocks its path. Some physicists believe the universe itself might currently rest inside a similar kind of shallow, temporary dip, a state called a false vacuum, rather than sitting in its truest, lowest, most stable possible energy state. If that theory is correct, the right kind of disturbance, potentially something as small as a single unlucky quantum event occurring naturally, somewhere, at some point across the entire universe, could theoretically knock the universe out of its current false stability and into its true, lower energy state. The result would not look like an ordinary explosion. Physicists describe it as a bubble of altered physics, forming at a single point and then expanding outward in every direction at the speed of light itself. Inside that expanding bubble, the fundamental rules governing particles, forces, and matter would shift into a completely different configuration, one likely incompatible with atoms, chemistry, or anything resembling structure as we currently understand it. Because this bubble would expand at the speed of light, nothing anywhere, no warning system, no telescope, no possible technology could ever detect it coming before it arrived. Light itself carries information no faster than the bubble's expanding edge, meaning the boundary would arrive at exactly the same instant as any possible warning of its approach. A civilization anywhere in its path would experience no gradual build-up and no final moment of realization. Existence would simply continue normally and then stop, everywhere at once, without any perceivable transition between the two states at all. Most physicists consider this scenario extremely unlikely within any time frame worth worrying about personally, and some research even suggests our particular universe might be more stable than early calculations feared. The idea persists in serious scientific literature anyway, precisely because it represents the purest, most extreme version of a threat requiring absolutely no warning whatsoever, a candidate for cosmic silence that would apply equally and instantly to every civilization across the entire universe at once, with no exceptions and no chance to prepare. Some researchers, faced with a growing list of dangers this severe and this difficult to detect in advance, have proposed a radically different explanation for the silence entirely, one that removes extinction from the equation completely and questions the nature of reality itself. Every explanation covered so far assumes the universe operates exactly the way it appears to: real stars, real distances, real physical laws governing everything from gamma rays to vacuum decay. A small but serious group of physicists and philosophers has proposed something stranger, an idea that would explain the silence without requiring any civilization to actually be destroyed at all. The simulation hypothesis suggests that what we experience as physical reality might actually be a highly detailed computer simulation run by a civilization vastly more advanced than our own, using computing power far beyond anything humans currently possess. Philosopher Nick Bostrom formalized this idea into a structured argument in the early 2000s. His reasoning does not claim we definitely live inside a simulation. It instead argues that at least one of three specific statements must be true. Either civilizations almost always destroy themselves before ever developing the technology needed to run such advanced simulations, or advanced civilizations exist but deliberately choose never to run simulations of their own ancestors for some reason, or a significant number of simulations already exist, meaning a randomly selected conscious mind, statistically speaking, would be far more likely to exist inside one of those many simulations than inside the single original reality that started the whole process. If a sufficiently advanced civilization could eventually run enormous numbers of detailed historical simulations, each one populated with billions of thinking, feeling minds unaware of their own simulated nature, then simple math suggests simulated minds would vastly outnumber minds living in the one original base reality. Under that reasoning, any individual conscious observer, including you right now, would statistically be far more likely to exist inside a simulation than inside the genuine original universe. Here is where this connects directly back to cosmic silence. If we exist inside a simulation built specifically to study or recreate a civilization's own early history, that simulation might only render the specific details relevant to its actual purpose. A simulation designed to study human history in careful detail might have no practical reason to also generate a fully detailed, populated galaxy full of alien civilizations stretching outward in every direction, the same way a detailed video game does not bother rendering the inside of a building nobody has walked into yet. Under this framework, the silence would not represent extinction, danger, or rarity at all. It would simply reflect the boundaries of what the simulation actually needed to include, a kind of cosmic set dressing, detailed enough to feel completely convincing from the inside, without requiring anyone to actually populate every star with a fully simulated society of their own. Most scientists treat the simulation hypothesis as fascinating but currently untestable, a philosophical thought experiment rather than a genuine scientific theory backed by observable evidence. It persists in serious conversation anyway, because it manages something few other explanations for the silence can claim, removing the fear of extinction entirely, while still leaving the deeper mystery of our apparent solitude fully intact. Whether or not reality itself turns out to be exactly what it appears to be, one far simpler and far more testable possibility remains standing quietly behind almost every theory covered in this story so far: the idea that life spreads easily across the universe, while the specific spark of true intelligence remains the genuinely rare and precious event. Step back and consider every living creature that has ever existed on Earth across nearly 4 billion years of unbroken biological history. Countless billions of species have lived, evolved, adapted, and eventually gone extinct across that entire span of time. Out of every single one of them, exactly one species ever developed the specific combination of traits needed to build a telescope, launch a satellite, or ask a question like the one driving this entire story. That detail forms the foundation of a theory that flips an earlier idea from this story on its head. The rare Earth hypothesis, covered several chapters ago, argued that complex life itself might be the rare, difficult step. A related but distinct idea argues something narrower and in some ways even stranger. Complex, multicellular life might actually be reasonably common across the universe, popping up wherever conditions allow it. True intelligence, the specific kind capable of abstract reasoning, tool building, and long-term planning, might be the genuinely rare event layered on top of it. Consider how many separate branches of complex life have existed on Earth without ever developing anything resembling human-level intelligence. Dinosaurs dominated this planet for well over 100 million years, an almost incomprehensibly long reign compared to the mere few 100,000 years modern humans have existed, and not a single dinosaur species ever showed clear evidence of building tools, controlling fire, or developing complex, symbolic language. Countless other successful, complex creatures, from ancient reptiles to early mammals, thrived for tens of millions of years, each without ever taking that same specific evolutionary path toward abstract thought. This suggests something genuinely uncomfortable buried inside Earth's own history. Complex, successful, thriving life does not automatically drift toward intelligence over enough time, the way water automatically flows downhill, given enough time and opportunity. Intelligence may instead require an extremely specific, narrow combination of evolutionary pressures, environmental accidents, and sheer chance, one that could easily fail to occur even across many billions of years of otherwise successful, complex biological history on a given world. If this theory holds true, it would reshape the entire meaning of the silence surrounding us. The galaxy might genuinely be teeming with complex, thriving biospheres, full of plants, animals, and elaborate ecosystems, without a single one of those worlds ever producing a creature capable of looking upward and wondering what those distant points of light actually are. Under this framework, humanity would not simply be rare in the way a difficult chemical accident is rare. We would represent something closer to an extraordinarily unlikely evolutionary lottery ticket, drawn just once out of billions of complex, successful species across our own planet's history alone, let alone across every other living world scattered throughout the galaxy. If true intelligence really is this rare and this fragile an outcome, an old, uncomfortable fear about being alone in the universe starts to look less like a tragedy and closer to something else entirely: a strange, unexpected kind of privilege. Most people who first encounter the Fermi paradox feel an immediate instinctive dread at the thought of being alone in the universe. Loneliness, on a cosmic scale, sounds like the worst possible answer to Fermi's original question. A closer look at several of the theories covered throughout this story suggests something surprising hiding underneath that fear. A version of being alone that might actually represent one of the better outcomes available. Consider what the alternative explanations require. A dark forest galaxy, filled with hidden, hostile civilizations waiting silently to eliminate any newcomer who reveals itself, would mean humanity's every broadcast, every radio signal, every accidental leak of technological noise into space carries genuine, serious danger. A universe governed by a brutal, still upcoming great filter would mean civilizations like ours regularly reach roughly our current stage of development, only to be destroyed shortly afterward by dangers of their own making. Compare those grim possibilities against a much gentler one. What if intelligence really is the rare, precious evolutionary event described in the previous chapter, and humanity simply happens to be one of the fortunate, early results of that rare event occurring successfully? Under this version of events, the silence would not represent a graveyard of failed civilizations, nor a forest full of hidden predators waiting patiently in the dark. It would represent something closer to genuine emptiness, a vast, quiet space still waiting to be filled, rather than a space already claimed by danger. Being early carries a very different emotional weight than being doomed. A civilization that arrives first, ahead of any dangerous neighbors, does not need to fear ancient predators lurking nearby, does not need to fear breaking some ancient rule it never knew existed, and does not automatically inherit the failures of countless civilizations who came before and collapsed under the weight of their own technology. This version of events also hands humanity something no other explanation in this story quite offers: genuine responsibility over an open future rather than fear of an already determined one. If nobody else has claimed the galaxy yet, then how humanity chooses to grow, expand, and handle its own increasingly powerful technology over the coming centuries would not simply decide our own fate. It could end up shaping the story of intelligent life across an enormous stretch of the universe, simply because so few other candidates currently exist to compete for that same role. None of this proves humanity will actually survive its own great filter, whatever specific danger that filter eventually turns out to be. It does suggest that the specific flavor of aloneness we appear to be experiencing right now might carry less horror and more quiet opportunity than the initial dread of the question first implies. Taken together, every theory explored throughout this story starts pointing toward the same narrow, urgent window of time, one that says less about the distant past or the distant future, and far more about exactly where humanity currently stands today. Pull every theory covered throughout this entire story into a single room, and a striking pattern emerges. Almost none of them point toward the distant past as the most important moment. Almost none of them point toward the distant future either. Nearly every serious explanation for the silence keeps circling back to roughly the same narrow window of time, the exact stretch of history humanity currently occupies right now. The grabby aliens theory suggests we exist unusually early in the universe's overall timeline, among the very first possible generation of expansion-capable civilizations. The Great Filter theory suggests humanity currently sits at, or dangerously close to, the exact technological stage where civilizations across the universe tend to disappear. The artificial intelligence risk, the engineered pandemic risk, and the nuclear weapons risk all cluster around this same specific era of human development, a species just barely powerful enough to threaten its own survival without yet being wise enough to fully guarantee its own safety. This clustering effect does not happen by accident. Every one of these dangers requires a very specific level of technological capability to even become possible in the first place. A species without industrial technology cannot trigger a runaway greenhouse effect. A species without advanced genetic engineering cannot accidentally release an enhanced pathogen. A species without sufficiently powerful computing cannot build an artificial intelligence system smarter than itself. Humanity crossed each of these specific thresholds only within the last century or two, an almost immeasurably small sliver compared to the 4.5 billion years our planet has existed. This means humanity is not simply living through an interesting moment in history. According to nearly every serious theory explored throughout this entire story, we may be living through the single most statistically significant window our species will ever experience, a narrow stretch of decades where the tools capable of ending everything have arrived, while the wisdom needed to fully control those same tools remains, at best, still catching up. None of the theories covered in this story offer certainty about how that window ultimately closes. Some point toward quiet relief, a filter already safely behind us, or a rare, precious kind of intelligence that already succeeded once and might succeed again. Others point toward genuine, sobering danger, a filter still waiting just ahead, patient, indifferent, and entirely unconcerned with how promising or well-intentioned any particular civilization happens to look right before it fails. What every single theory agrees on, regardless of how comforting or how frightening its specific conclusion turns out to be, is the underlying importance of exactly where we currently stand. Not our distant ancestors climbing down from trees, not some far future descendant living peacefully among the stars centuries from now. This specific era, this specific level of technology, and the specific choices made by people alive on the planet right now. That shared conclusion raises an obvious, practical question. If this really is the narrow window that decides everything, what exactly separates a biological failure from a technological one? And does knowing the difference actually change anything about how humanity should respond? Not every candidate for the Great Filter behaves the same way, and the difference matters enormously for how humanity might actually respond to the danger. Biological filters operate slowly, shaped by evolution across enormous stretches of time, largely outside anyone's direct control. The jump from simple to complex life, discussed several chapters ago, represents this kind of filter clearly. No individual choice speeds it up or slows it down. It either happens, given the right combination of chance and circumstance stretched across hundreds of millions of years, or it simply does not happen at all. A civilization cannot vote to accelerate evolution, cannot legislate its way past a biological bottleneck, and cannot simply choose to make intelligence appear faster through effort or willpower alone. Technological filters work in almost the opposite way. Nuclear weapons, engineered pandemics, runaway climate collapse, and uncontrolled artificial intelligence all share one crucial feature biological filters lack entirely. Every single one of them results directly from deliberate choices made by specific people at specific moments, using specific tools those people built themselves on purpose. Nobody accidentally evolves into a species capable of splitting atoms. Someone, somewhere, has to choose to build that capability, refine it, and eventually decide exactly how carefully or how recklessly to handle it. This distinction carries real, practical weight. A biological filter offers humanity no meaningful lever to pull. If the hardest step in the universe truly was the ancient leap from simple to complex life, there is nothing left for humanity to actively manage about that particular danger, since we already cleared it successfully billions of years ago without any conscious effort involved at all. A technological filter works completely differently. Every technological danger covered throughout this story remains, at least in theory, something humanity retains some meaningful amount of control over, right now, in the present moment. Nuclear arsenals can be reduced through careful negotiation and continued restraint. Dangerous genetic research can be regulated, monitored, and conducted with stronger, more consistent safety protocols. Artificial intelligence systems can be developed more slowly, more carefully, and with far more serious attention paid to alignment and safety before deployment, rather than racing forward purely for competitive advantage. Here lies the small but genuinely important sliver of hope buried within an otherwise unsettling set of theories. If the Great Filter really does turn out to be technological rather than biological, then unlike almost every other danger explored throughout this entire story, this specific kind of filter is not something happening to humanity from the outside. It is something humanity is actively building with its own hands, one decision at a time, which means it remains, at least partially, something humanity can still choose to build more carefully. That distinction between what we cannot control and what we still can raises an obvious, urgent question. If certain dangers really do remain within our own hands to manage, what specific signs would actually tell us whether humanity is approaching its own filter right now before it becomes too late to change course? If a civilization really is approaching its own great filter, would it even recognize the warning signs while there was still time left to change course? Or would those signs simply blend into the ordinary background noise of everyday life until it was already too late? Researchers studying existential risk have identified several patterns worth watching closely, drawn partly from history and partly from careful modeling of how dangerous technologies tend to behave once they spread widely enough. One consistent warning sign involves what researchers call a widening gap between power and wisdom. Every dangerous technology explored throughout this story, nuclear weapons, engineered pathogens, uncontrolled artificial intelligence, shares a troubling pattern. The raw destructive or disruptive capability of these tools tends to grow far faster than the safety systems, international agreements, and shared understanding needed to manage them responsibly. When capability sprints ahead, while caution and coordination struggle to keep pace, researchers consider that gap itself a serious warning sign, regardless of which specific technology happens to be widening it at any given moment. A second warning sign involves competitive racing dynamics. Throughout history, dangerous technologies have often advanced fastest, not when a single group carefully weighed the risks, but when multiple rival groups, nations, or companies felt pressured to develop something powerful quickly, out of fear that a competitor would otherwise gain a decisive advantage first. This kind of race tends to reward speed over caution, since any single participant who slows down to prioritize safety risks, losing the race entirely to a rival willing to move faster and cut more corners. A third warning sign involves what researchers call diffusion of responsibility across an increasingly complex, interconnected system. As dangerous technology becomes cheaper, more widely available, and easier to access, the number of individuals capable of causing serious harm grows steadily larger, while any single person's sense of personal responsibility for the overall outcome tends to shrink correspondingly smaller. A danger that once required an entire government's resources to create can eventually become achievable by a small, motivated team, or even a single, sufficiently skilled individual working largely alone. None of these three warning signs guarantee catastrophe on their own. Civilizations, including our own, have successfully managed dangerous technology before, through careful international agreements, shared safety standards, and hard-won lessons learned from earlier close calls. Nuclear weapons, despite decades of genuine danger and multiple documented near misses, have not yet been used again in the 80 years since their creation. A real, meaningful accomplishment built on sustained caution and continued restraint. What makes these particular warning signs valuable is not certainty about the future. It comes from giving researchers, policymakers, and ordinary people something concrete to watch for, rather than facing an abstract, unfocused sense of dread about dangerous technology in general. Recognizing the specific pattern, a widening gap between power and wisdom, a dangerous competitive race, and a shrinking sense of individual responsibility, offers something the ancient extinctions covered earlier in this story never could: an actual chance to notice the danger building in advance, and to respond before the pattern fully completes itself. Recognizing these signs, raises the next obvious question directly. If these warning signs really can be spotted in advance, what do the scientists who study this exact problem for a living actually recommend humanity do about it? Faced with a growing list of theories, warning signs, and uncomfortable statistical arguments, a serious and growing community of scientists, philosophers, and policy researchers has spent the past several decades asking a very practical question. Given everything explored throughout this story, what should humanity actually do right now? Their answer rarely involves panic or despair. Instead, most researchers in this field, often working under the broad label of existential risk studies, argue for a specific, deliberate shift in how humanity prioritizes its own long-term survival, treating it as seriously as any other major global challenge, rather than as a distant, abstract worry reserved for science fiction. One consistent recommendation involves what researchers call differential technological development, the idea of deliberately accelerating safety research and protective measures faster than the raw, dangerous capabilities of a new technology, rather than allowing both to develop at the same uncontrolled pace. Applied to artificial intelligence, this means investing heavily in alignment research and safety testing alongside, or even ahead of, raw capability improvements, rather than treating safety as an afterthought bolted on only once a powerful system already exists. A second recommendation focuses heavily on international cooperation, specifically around technologies capable of causing global, irreversible harm. Nuclear weapons offer a useful, if imperfect, historical model here. Decades of careful arms control agreements, hotlines between rival governments, and shared verification systems did not eliminate nuclear danger completely, but they meaningfully reduced it compared to a world with no coordination or communication at all. Researchers argue similar frameworks, built early and taken seriously, could help manage newer dangers like engineered pathogens and advanced artificial intelligence before a genuine crisis forces those same conversations to happen under far worse, more rushed conditions. A third recommendation involves something researchers call resilience and redundancy, essentially building backup systems and safeguards specifically designed to help civilization recover even if a serious catastrophe does occur, rather than focusing purely on prevention alone. This includes efforts like protected seed vaults, carefully maintained backup food and medical supplies, and even serious research into rebuilding critical infrastructure quickly after a major disaster, treating civilization less like something that simply cannot fail, and more like something worth actively protecting against failure through deliberate preparation. Perhaps the most consistent theme across nearly every serious researcher in this field involves timing itself. Nearly all of them argue that the specific window explored throughout the previous several chapters, this narrow stretch of decades where humanity's raw technological power has outpaced its collective wisdom, represents the single most important period to get this right. Waiting until a dangerous technology has already caused serious, irreversible harm before taking safety seriously removes the very advantage that makes prevention valuable in the first place, the ability to act before the worst outcome actually happens. That final point carries an uncomfortable implication worth sitting with directly. If prevention really does require acting before absolute proof of danger exists, waiting patiently for undeniable evidence before responding might not represent caution at all. It might represent the single most dangerous strategy available. Throughout history, most major decisions wait for solid evidence before demanding serious action. Governments typically wait for clear data before changing major policy. Companies typically wait for proven results before committing significant resources to a new direction. This instinct makes sense for most ordinary decisions, where waiting costs relatively little and getting it wrong causes only limited, recoverable harm. Several of the dangers explored throughout this entire story break that ordinary logic completely, and understanding exactly why reveals one of the most important and most difficult lessons buried inside the entire Fermi paradox. Consider the specific nature of an existential risk. a danger capable of ending civilization entirely rather than merely damaging it. Nearly every other type of risk humanity has ever faced allows for a valuable process scientists call iterative learning. A bridge collapses. Engineers study exactly why, and every future bridge gets built safer as a direct result of that specific failure. A disease outbreak spreads. Researchers study its exact spread pattern, and future outbreaks get contained more effectively using lessons learned directly from the last one. Existential risks offer no equivalent second chance. If humanity waits for undeniable proof that an artificial intelligence system has become genuinely, irreversibly dangerous before taking the threat seriously, that proof would likely arrive only after the danger had already become impossible to contain or reverse. If humanity waits for undeniable proof that a specific engineered pathogen can cause a global pandemic before restricting the research capable of creating one, that proof would likely arrive in the form of the pandemic itself, already spreading uncontrolled across the planet. There is no opportunity to study the failure carefully and apply the lesson forward, since the entire population capable of learning that lesson would already be gone. This creates what researchers call an asymmetry problem. Acting cautiously against a threat that ultimately turns out to be smaller than feared costs relatively little, some wasted resources, some slowed progress, some unnecessary caution that later research reveals was not strictly needed after all. Waiting for proof against a threat that turns out to be exactly as dangerous as feared costs everything, with no opportunity for recovery, correction, or a better attempt next time. Nearly every civilization capable of reaching humanity's current level of technology would likely face this exact same uncomfortable asymmetry, the temptation to wait for clear, undeniable proof before taking a serious, difficult, expensive precaution against a danger still framed as merely theoretical. If waiting for proof really does represent the single most tempting and single most dangerous strategy available at this exact stage of development, it would offer one final, quiet, universal explanation for why the galaxy might stay this silent, not through malice, not through inevitability, but through countless individual civilizations, each reasonably, understandably, waiting one measured step too long before finally choosing to act. Every theory, every warning sign, and every uncomfortable statistic explored throughout this entire story eventually leads back to one single, unavoidable question. The exact same question this whole journey began with, only heavier now, and impossible to ignore any longer. Every path through this story leads back to the same three words Enrico Fermi first spoke over lunch nearly 80 years ago. Where is everybody? We now understand why that question refuses to fade quietly into the background. A galaxy holding 200 billion stars, filled with planets far more common than anyone once assumed, should not sit this quiet. The Drake equation, even wearing its most cautious, conservative numbers, keeps predicting company rather than solitude. Decades of careful listening, using instruments more sensitive than Fermi himself could have imagined, keep returning the exact same answer: nothing. Three broad possibilities remain standing after everything explored throughout this entire journey, and each one carries its own weight, its own comfort, and its own quiet warning. We might simply be early. The grabby aliens theory suggests the universe has only just begun producing the stars it will eventually create across trillions of future years, meaning intelligent, expansion-capable civilizations may still be exceptionally rare and young across the entire cosmos, with humanity standing somewhere near the very front of an enormous, unfolding story rather than lost somewhere in its crowded middle chapters. We might simply be rare. Complex life may bloom easily across countless worlds, filling the galaxy with thriving, successful ecosystems, while true intelligence remains the genuine evolutionary lottery ticket, drawn only once across billions of species and nearly 4 billion years of biological history right here on Earth alone. Under this possibility, the silence would represent genuine emptiness rather than danger, a universe still waiting for company rather than one actively hiding it. We might simply be running out of time. A great filter, biological or technological, may sit directly ahead of every civilization that reaches roughly our current stage of development, a stage defined by exactly the kind of raw destructive power explored throughout this entire story: nuclear weapons, engineered pathogens, runaway climate collapse, and artificial minds racing ahead of humanity's own collective wisdom to control them safely. Nobody currently alive can say with total certainty which of these three possibilities actually describes our universe. That uncertainty itself carries an important practical lesson. 1. Every theory in this story eventually points back toward, regardless of which specific explanation ultimately turns out to be correct. If we are early, humanity's choices over the coming centuries could shape the story of intelligent life across an almost unimaginable stretch of cosmic time. If we are rare, that same responsibility grows even heavier, resting on a species that may represent one of the only successful attempts the universe ever produces. If a filter really does wait just ahead of us, then every single decision made by people alive today, right now, carries more weight than almost any generation before us ever had to carry. Fermi asked his question over lunch, never expecting it to still be unanswered 80 years later. The silence he first noticed has only grown deeper since then, stretching further into space and further into the record of everything we have failed to hear back. Somewhere out there, across 200 billion stars, the answer is still waiting. Whether humanity lives long enough to actually find it may depend less on the universe itself and more on exactly what we choose to do with the narrow window of time we have been given right now.